looking at each of these graphs, it's so important that we understand the difference between the graphs that we are looking at and whether we're looking at the original function or the derivative. And all these big ideas come together in one conversation. If my original graph is a straight line, that is a constant value. Sometimes we call that x to the 0 power, because anything to the 0 power is? Anything to the 0 power is? 1. Say that again. Anything to the 0 power is? 1. Yeah. So that means that it's a constant. So when I go to take the derivative of a constant, what is it? It is 0. So here's our graph of 0 right here. So 1 matches up with D. You okay with that? All right. When we are looking at a linear function, our linear function is x to the first power. Our derivative is going to be one level lower. So it's going to be x to the 0 power. X to the 0 power is 1, right? So our derivative graph is going to be a constant. H. Are we okay with that? Yeah? All right. Number 6 is H. I had to renumber. So make this A, B. Oh, darn it. Hold on a minute. A, B, C, D. Oh, snap.
Just leave it the way it was. Sorry, that sounded bad. I meant it. Please leave it the way it is.
So we'll leave this as D.
Yep. No, right over it. I to see.
And we'll leave this as G. I hate Word. What's this one supposed to be?
D.
And this one should be G. And this one should be H. And this one should be J.
Okay.
And this one should be K.
Yep.
Are you okay with that? I hate Word. So honestly, that is Word's fault, because every time we hit save, anybody ever deal with that with Word? Every time you hit save, what does it do? It updates it. So we'll call that one J. You like that better? Yeah? Are we good to move on?
Yeah.
I'd rather not have to speak over everybody. Thanks. All right, continuing up our levels of polynomials. What do we call this? What kind of graph is a parabola for? A quadratic. So when we talk about the quadratic, our derivative of a quadratic is going to be linear. So I know right away this linear graph is going to be my derivative of my quadratic. Now I have to be careful with my cubic, because this is a cubic graph in 7, and this is a cubic graph in 8. So when I go to find the ones that match, I have to pay careful attention to the graphs that are going to give me the information that I need. This cubic graph has a min and a max, a local min and max, where the derivative is equal to 0 at like negative 1/2 and at positive 1. This one only has this hiccup. It's not necessarily a minimum or a maximum because the graph doesn't have a hill or a valley. So I don't have values above or below that critical point. So when I look at my two quadratic graphs, does it make sense that this one, B, matches here because I have a 0 at 1 and negative 1/2. This one matches with A because that 0 sits right at 0, 0.
Which one was A?
7 is A. 8 is B. All right, so for these last couple graphs that I have left, we should really get the easy one out of the way. And the easy one is not the one that you think is the easy one. Why is that the easy one?
Because it's the same thing.
Yeah, because take a look at the sign in the back. The derivative of e to the x is e to the x. So my derivative of e to the x is e to the x. So this one is g. If we're continuing on our pattern of increasing powers of x, this quartic graph is going to have a derivative equal to 0 here. And something interesting happening there. So we have, here's my 0. Here is my cubic. That is my one level less function. So see the difference between my derivative is equal to 0 and just where I have my derivative changing concavity. This ends up being a point of inflection where my derivative goes from getting bigger to getting smaller, increasing to decreasing. So of course, the only one we have left is, do you recognize this as a sine function? And we know that if I have the sine of x, my derivative is going to be the cosine of x. So this one's E, this one was H. Mental note, go back into the file and fix my ABCs. Sound okay? All right. So on the back, I gave you a quick review, basically, of the unit. So I want you to think back to your geometry brains. In your geometry brains, every single time that you did a proof, or every time that you said something was, you had to provide some kind of justification. I know this is true because this theorem says this. Vertical angles are congruent because of vertical angle theorem. And some of the angles in a triangle is 180 degrees because of triangle sum theorem. Triangles are congruent because of side, side, side. So you have to have some kind of... So when we talk about the three theorems that we've learned in this unit in calculus, our mean value, our intermediate value, and our extreme value theorems are the ones that justify why we can say the things that we can say. Our mean value theorem is the one that says if your function is continuous over an interval and differentiable, then there's got to be a point where the average rate of change and the instantaneous rate of change are the same. So you can find the average rate of change, i.e. slope, and you can set that value equal to the derivative, and then you can figure out where the instantaneous rate of change is the I was on your last quiz, I'm about to pass by. Your intermediate value theorem is your justification for how you can say, if you have a function continuous over a and b, every output value between f of a and f of b must exist. If it's continuous, no one says it has to be differentiable, but if it's continuous, that means that if I have an output value here and an output value here, everything in between must exist. What's on this quiz, when we talk about the extreme value function, is if you have a function that's continuous over this interval, there's got to be at least one high point and one low point on that closed interval. And that closed interval is where I'm talking about just between A and B. There's got to be at least one high, one low. When we find what those highs and lows are, we're looking at where does our derivative equal 0, or where does it not exist? We call that the first derivative test. If my output of my function, if my derivative is positive, my function is increasing. If my derivative is negative, my function is decreasing. So when I take my sign of my derivative and I create this sign chart where I add as many critical point columns as I need, and I look at everything on this side, I look at everything on that side, and I can validate whether it's increasing or decreasing. Now, if they give us a graph, I don't need to do that noise. If they give us an equation, I need to find the derivative to find where those critical points are. If I'm looking at a graph, I can just see it on my graph. When I start talking about concavity, that's where I'm looking at the rate of change of my rate of change. I'm looking at, and that's where we start talking about that second derivative. And I'm looking to see if f of x is getting steeper or if it's getting flatter. And my points of inflection are where my concavity changes. And this is something that I want to make sure that you all have here. If it's concave up and increasing, my curve looks like this. If it's concave up and it's increasing, it looks like that. If it's concave down and decreasing, it looks like that. And what I want you to do is, if it helps you to take your straight edge or a ruler, make some sense of those tangent lines. So if I look at those tangent lines, I can take a look at how each of my tangent lines is moving from being 0 to positive to even more positive. And I'm looking at that tangent line getting steeper and steeper and steeper. It's concave up. The derivative, the value of my slope, is increasing. If my derivative is positive but flattening out, then my derivative value is getting smaller and smaller and smaller. So even though my derivative value is positive and my derivative value here is positive, I'm actually decreasing because I'm going from super positive to 0. I'm getting smaller. So think about not just the value of your derivative, but how is it changing? I'm increasing at an increasing rate. Here I'm increasing at a decreasing rate. If I have a value that's concave up, but it's decreasing, my graph looks like this. Because what ends up happening is my tangent line even though my function is decreasing, my tangent line, my value of my tangent line is negative, but it's getting bigger. If I have a concave down, I have negative slopes, and they're getting more and more and more negative. So looking at the slope of and the behavior of my graph is one thing. Looking at the sign of my tangent line is another thing. Look at whether that sign and how it's changing. If I'm concave down, but my line is getting steeper and steeper and steeper and steeper. All right, with your group, take a look at this graph and estimate the interval on which g of x is increasing, decreasing, where it has local extrema, and where the inflection points are. Turn and talk. Where my derivative of my derivative, where my second derivative equals 0, that's where my concavity changes. So I'm not looking at the graph of the original function, I'm looking at the graph of its derivative. So here, my derivative value is negative. It's very negative, and it's getting less negative. Here my derivative value is equal to 0. If you want to imagine what this looks like, this is a curve that's very negative and getting less negative. So this red story here is this. Very negative derivative. Here it is. And my derivative value is increasing. My derivative value is getting bigger and bigger and bigger. Because my derivative value is increasing, getting bigger and bigger and bigger, it's going to be concave up, like that. My original curve. Go.
Wouldn't it be at where 0 is too? Wouldn't that be a inflection as well?
So because this is a graph of my derivative, not my original function, every time that my derivative is equal to 0, that's a min or max of my original graph. That's where it equals 0. Every time I have a hill or a valley in my derivative graph, that means my second derivative is equal to 0. That's a point of inflection. So this right here, and this right here are mins and maxes.
No, but I'm talking about the one in the middle. At 0, 0.
Yeah, I didn't get there yet. So we're talking about, just let me get there. So my derivative graph, very negative, getting less negative, hits 0. My derivative here is positive, which means my original graph has now turned around and is going up. It's still increasing, meaning that my derivative is positive. Here it is positive, but it's getting steeper, or it's increasing, increasing, increasing. When my derivative graph stops increasing, it's starting to decrease. So my derivative value is 0, 1, 2. 0 is my slope, 1 is my slope, 2 is my slope. See how it's getting steeper? But now it starts to decrease. So this is where, instead of this graph traveling up this way, it's going to turn, because now I'm going to have a decrease in my slope. My slope value is still positive, it's just not as positive. So it's still positive, I still have a positive derivative, it's just not as positive. Now we want to talk about what's happening here. My derivative value never goes negative. My derivative, my function doesn't change direction. My derivative is positive, it hits 0, and then it goes back to being positive. So that's one of these hiccups in the graph that look like this. It doesn't change direction, so it's not a minimum or a maximum. This is not a minimum or a maximum because my derivative doesn't change sign. I don't go from positive to negative. In order to find a minimum or a maximum, that's where my derivative changes sign. This is a min or max, this is a min or max, because my derivative goes from negative to positive, positive to negative. My derivative does not change sign in that middle part, it's always positive. Once my derivative graph hits 0 and switches from being positive to negative, I know I have found a minimum or a maximum. Right. So where is my original graph increasing? My original graph is increasing once I have this point of inflection, because my graph is coming down, my derivative is negative, my derivative is negative. Here my derivative is 0, so any place that my derivative is positive, my function is increasing. That story up here. If my derivative is positive, my function is increasing. So any place that has a positive derivative, my function is increasing. So from negative 3 all the way up until 3, that function is increasing. My original function is growing and getting bigger. Now, it's the same as with the bottle and the water. When you're pouring the water in the bottle, you could be increasing at a decreasing rate, you could be slowing down, you could be speeding up. But my original function is still increasing anytime that my derivative is positive. Anytime that my derivative is negative, my function is decreasing. So from negative infinity to negative 3. And from 3 up to positive infinity, I have a negative derivative, which means my function is decreasing. Your local extrema is going to be at over negative 3 up 0. and over positive 3 up 0. And since I have a negative to a positive, I know this one's a minimum. Since I have a positive to a negative, I know this one's a maximum. And draw yourself a little picture to see if I have a negative slope that goes to being positive, or if I have a positive slope that goes to being negative. That's my min and max. The inflection points are going to be right here where my concavity changes. Negative 2, 2, and positive 2, 2. All right, with your group, talk it out. Go. Continuing our conversation of our bottle problem. When we talk about each of these graphs, now, the graph we were just looking at was the graph of the derivative. This is a graph of the actual original function. So this is the graph of the height over time. So if my graph is linear, that means that that height of the bottle is changing at a constant rate of change. That only happens when the sides of my bottle are completely straight. So because the sides of my bottle are completely straight, my height is growing at a steady rate. That's why this is going up at a steady rate. Once I reach this point, and it goes up faster because the walls of the bottle are skinnier, then that's why it goes up at a faster rate. The interesting thing to do is look at the graphs that are opposites of each other. So if you look at graph E and graph C, you can see how they look as the sides of the bottle either come in or go out. So if I look at graph E, I'm increasing at an increasing rate. That's because my water's going up, but it's going up faster and faster and faster because the sides of my bottle are skinnier. C is going to be the opposite of that. I'm increasing at a decreasing rate because my water's still going up, but not as fast. Anybody want to talk about any of these? All right. The bottle should look like this. Here is linear. And the bottle has to be kind of fat because it's going up at a slow rate. So you would have a wider bottle. The bottle's getting skinnier because it's increasing at an increasing rate. This is where the sides of my bottle narrow. This third section of my bottle is where the neck of my bottle is super skinny, and it goes up. But at a constant rate, so it's straight walls up and down. Okay, on the back, let's talk about the middle two graphs first. The middle two graphs are graphs of our original functions. There's never a time that it's positive concavity. And we can talk about the concavity of these original functions, and that's where I can say it's down like a frown. It's never up like a cup. So the whole time it's negative. And there's no times when my concavity changes. I don't have any points of inflection on that graph. On this sine graph, I have positive positive concavity here. I have positive concavity here. I've got negative concavity here. Now, feel free to go ahead and think about that in terms of the derivative. Here my derivative is negative, but my derivative value is increasing. Every single time that my derivative value is increasing, that's where I end up with up like a cup. As soon as I cross this point here, my derivative value is decreasing, and that's where I have my down like a frown. My slope of my tangent line is the derivative. So if you run the derivative along the graph, you can see decreasing and increasing. If you're given the graph of the original function, use the graph of the original function to help you determine concavity. Does that make sense? Okay. Now let's talk about the ones where the derivative is increasing or decreasing. And I have here a rough sketch of what the original function. Here my derivative is negative. Here it is negative. And I sketched this because my derivative is getting less and less negative, and right around here, my derivative is equal to 0. So my derivative has positive concavity as long as my derivative is increasing all the way up to this point here. When my derivative is decreasing, I have negative concavity. When it's increasing, I have positive concavity. When it's decreasing, I have negative concavity. My points of inflection are going to be my critical points, either where I cannot take the derivative of my function or where the derivative of my function is equal to 0. Let's talk about the last one. When my derivative is increasing, when my derivative is negative, but my derivative value is getting bigger, bigger, I have positive concavity. My derivative is getting smaller, I have negative concavity. When my derivative is getting bigger, I have positive concavity. Are we okay? You want to ask a question?
I don't think so. It's just we're trying to figure it out.
Okay, go ahead.
Doesn't it go from down frown, double cup, down frown, and then it ends on?
Your graph is different from the graph of your derivative. You're looking at the graph of your derivative. Your derivative value is negative. So this graph, if I were to sketch it, starts off like this. Because my derivative is getting bigger, my derivative value. I have a slope of -3, I have a slope of -2, I have a slope of -1, I have a slope of 0, I've got a slope of 1. That whole story looks like this. A slope of -3, a slope of -2, a slope of -1/2, a slope of 0, a slope of 1. So this whole story looks like this because it's my slope. It's the value of my slope. -3 is the slope of the tangent line on my original graph. -1 is the slope of my tangent line on my original graph. 0 is the slope of my tangent line on my original graph. So where my derivative is equal to 0, when my derivative changes from positive to negative, that's a minimum value. When I'm talking about my concavity, I'm still going up, 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 up. I look at this function and I'm expecting it to go up, 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 up like a cup. But then all of a sudden, this happens. And my derivative stops increasing. So instead of it doing what I'm anticipating it doing, it ends up leveling out. Now my derivative is still positive. I don't have a min or max until my derivative is equal to 0. Once my derivative is equal to 0, then that's when it starts going down. So it becomes super important for us to pay attention to whether or not we are looking at the graph of the derivative or the graph of the original function. Okay? All right.